My name is Michio Kaku, and today I want to take you on a journey backward in time, farther than the dinosaurs, farther than the first stars, all the way to an era when the universe itself was still learning how to build order out of chaos. Thanks to the remarkable power of the James Webb Space Telescope, astronomers have uncovered a new and unexpected side of the early universe, and what they found has dramatically reshaped our picture of how galaxies, those sparkling islands of stars, first emerged from the cosmic darkness. When most people imagine galaxies in the early universe, they picture miniature versions of the Milky Way, elegant spirals, softly rotating, quietly gathering stars. But the truth, revealed in exquisite detail by Webb, is far messier and far more dramatic. More than 250 young galaxies, examined by a team at the University of Cambridge, have shown us that the early cosmos was not a peaceful cradle of forming structures. It was a storm, a cosmic storm filled with swirling gas, violent collisions, and unstable newborn systems struggling to find balance. These galaxies weren't the calm, rotating disks many had assumed. They were chaotic, clumpy, and turbulent. So turbulent, in fact, that the idea of an orderly disk was the exception, not the rule. Imagine a universe only 800 million to 1.5 billion years old. Barely a child in cosmic terms. The first stars have already lit up the darkness, the first galaxies have taken shape, and the fog of the early universe, the haze left after the Big Bang, has begun to lift. And yet, in this era, structure is only beginning to emerge. Gravity is trying to sculpt order, but the raw material, thick, unstable clouds of gas, is resisting. Everything is in motion. Everything is trying to settle, but nothing is quite settled yet. Using JWST's NIRCam instrument in its GRISM mode, astronomers were able to capture faint light from ionized hydrogen, gas that glows as it moves through young galaxies. This allowed them to map the internal motions of these galaxies with clarity no other telescope in history could provide. And when they looked deep into that early epoch, what they saw wasn't smooth rotation. It wasn't the elegant cosmic ballet many expected. Instead, gas was swirling in different directions, clumping into irregular shapes, and refusing to form the kind of organized disks we see in galaxies like our own. Only a small minority showed even the earliest hints of rotation. Most appeared more like cosmic tempests, galactic thunderstorms filled with unpredictable flows and unstable structures. For decades, astrophysicists debated how quickly galaxies in the early universe settled into disks. Some thought it happened rapidly, within a few 100 million years. Others insisted it must take longer. But until now, the data sample was simply too small. Previous telescopes could only observe the brightest, most massive early galaxies, the rare outliers that looked surprisingly mature for their age. Those galaxies misled us. They gave the impression that early disks were common. Webb has now shown us the truth. Those well-organized galaxies were the cosmic oddities. The galaxies typical of the early universe were unruly, energetic, still finding themselves. As lead researcher Dr. Lola Danhav commented, "We don't just see a few spectacular outliers. We looked at an entire population, and most are still chaotic, with gas puffed up and moving in all directions." For the first time, we have a statistical portrait of the early universe, not just its brightest stars, but its ordinary members. And that portrait reveals a universe defined by motion, disorder, and rapid transformation. Now, why does this matter? Why should we care whether galaxies were chaotic or organized a billion years after the Big Bang? Because this discovery fundamentally reshapes our understanding of galaxy formation. For decades, theoretical models predicted that early galaxies should be unstable. They should be full of gas, they should be turbulent, but observational evidence never matched theory until now. Webb has closed that gap, providing proof that galaxies don't begin their lives as orderly structures. They evolve into them. In many ways, it's like watching history unfold. These chaotic galaxies represent a missing chapter between two major eras. The epoch of rayonization, when the first galaxies illuminated the universe, and the later era known as cosmic noon, when star formation reached its peak. For years, we've wondered what the galaxies in that transitional phase truly looked like, and now we know they looked like storms still learning how to become galaxies. But to understand why they look this way, we need to look at the physical forces at play. First, early galaxies contained extraordinary amounts of gas, far more than the galaxies we see today. And gas, when present in large quantities, behaves unpredictably. It can collapse, fragment, churn, and surge in response to the slightest disturbance. Instead of forming stable disks, gas in these young systems moved in swirling flows, constantly stirred by the energy of star formation and gravitational interactions. Second, the early universe was crowded. Galaxies collided far more frequently than they do today. In fact, many of the galaxies Webb observed were likely in the middle of ongoing mergers, galactic dances that injected enormous energy into their structures. Each collision disrupted any developing order, making it even harder for rotation to take hold. Star formation bursts, triggered by those interactions, fed back into the chaos, heating gas, pushing it outward, and preventing it from settling. Third, disk formation is not instantaneous. It is a gradual, delicate process, a dance between cooling gas, gravity, and time. For a galaxy to form a rotating disk, its gas must lose energy and settle into a thin plane. But in the early universe, everything was too dynamic, too hot, too energetic for this to happen quickly. Webb's data shows that rotation becomes more common later as galaxies grow in mass and interactions mellow. This paints a fascinating picture. Our universe, in its youth, was not a quiet architect. It was a restless artisan sculpting galaxies through motion and disorder. Order emerged only slowly through the calming effect of time. And perhaps the most profound realization is this: these chaotic galaxies may resemble what the Milky Way looked like long before it became the graceful spiral we call home. When we peer into these distant systems, we are looking at our own cosmic childhood, an early snapshot of the forces that shaped everything we see in the night sky. But this is only the beginning. Our investigation is far from over. In the next part of our journey, we'll explore why this discovery rewrites key assumptions in astrophysics, what it means for our models of cosmic evolution, and how this chaotic portrait of the early universe fits into the grand story of galactic history. Your history, my history, the history of everything in the cosmos. When we look deeper into this discovery, we begin to understand that the early universe did not simply permit chaos, it required it. Chaos was not a flaw in the system, it was the engine driving evolution. And this realization forces us to rethink one of the most fundamental assumptions about cosmic history, that galaxies formed quickly into stable structures. For decades, astronomers looked at a handful of massive, bright early galaxies and believed they were snapshots of normal galactic youth. Those rare objects tricked us. They made the early cosmos look cleaner, calmer, more mature than it actually was. But Webb, with its extraordinary sensitivity, has now revealed the majority, the ordinary galaxies, the common ones, the ones that truly tell the story of the universe. This is why large statistical samples matter. For the first time, we can see beyond the brightest jewels of the early cosmos and into the crowded field of everyday galaxies, the galaxies that actually shaped cosmic history. And what we see is consistent with the predictions of decades of theoretical physics. The young universe was unstable, full of motion, and overflowing with raw material. The Cambridge team's dataset doesn't just confirm isolated theories, it verifies the theoretical framework that cosmologists have been building for years. In many ways, this discovery is the missing observational chapter that ties the physics together. Think of it this way. The early universe was like a construction site. Buildings don't appear fully polished. They start as piles of steel, concrete, and scaffolding, loud, noisy, full of dust and activity. Over time, the structure takes form, the noise quiets, the building stabilizes. Galaxies follow the same blueprint, except their construction site spans hundreds of millions of years, and their scaffolding is made of gas clouds, dark matter, and gravity. Now let's break down the physical processes that shape these chaotic early galaxies, because understanding them reveals why this discovery matters far beyond the galaxies themselves. First, gas fractions. In the early universe, galaxies contained enormous amounts of gas, far more than we find in galaxies today. Gas is the fuel of star formation, but it is also notoriously unstable. When you pile too much gas into a galaxy, it becomes turbulent. It collapses in some regions, expands in others, and reacts violently to any disturbance. This is why these early galaxies look clumpy and irregular. The gas simply couldn't settle. Instead of forming smooth rotating disks, the gas moved in chaotic flows, eddies, swirls, and streams driven by gravity and feedback from newborn stars. Second, mergers. The early cosmos was far denser than the modern universe. Galaxies were packed closer together, drifting through space like ships in a crowded harbor. Collisions were common, inevitable, and often violent. When two galaxies collide, gravity pulls their gas clouds in every direction, tearing structures apart and injecting energy into the system. Any attempt to form a stable disk is interrupted. Any emerging rotation is disrupted. Webb's observations show the unmistakable signatures of these interactions: asymmetric gas flows, off-center clumps, and velocity fields that refuse to align into a coherent rotation. Third, star formation feedback. Every time a massive star is born, it releases an intense burst of energy, radiation, stellar winds, and eventually supernova explosions. In a young gas-rich galaxy, these processes act like pressure valves, repeatedly kicking gas upward, outward, and away from the forming disk. Imagine trying to calm the surface of a lake during a thunderstorm. Every drop of rain disturbs the water. In early galaxies, every new star shook the structure. Star formation didn't build order, it magnified the chaos. Fourth, the gradual settling of disks. Only later, when galaxies gained mass, when they cooled, when collisions became less frequent, did the gas finally begin to settle into the classic rotating disks we recognize today. What Webb shows us is the timeline. Disk formation isn't early, it's late. Order doesn't precede chaos, it emerges from it. This discovery has enormous implications for our models of cosmic evolution. For years, simulations predicted that turbulence was dominant in early galaxies, but the lack of observational evidence created uncertainty. Now, those models gain powerful confirmation. They can be refined, expanded, and made more accurate than ever before. And with accurate models, we can reconstruct the story of our own galaxy with far greater confidence. Because here is the profound truth. When we look at these young galaxies through Webb's eyes, we are looking into a mirror. We are seeing echoes of the Milky Way's earliest chapter, a chapter we could never witness directly. Our galaxy, now a graceful barred spiral, was once a turbulent, irregular storm of gas and starbirth. The elegant structure we see today, with its arms and its rotating disk, is the result of billions of years of evolution out of chaos. This discovery also solves a long-standing puzzle about the relationship between early galaxies and two major cosmic eras. The first is the epoch of Ryanization, when the first stars lit up the universe and ended the cosmic dark ages. The second is cosmic noon, the period of peak star formation several billion years later. Until now, the connection between these two eras was foggy. How did galaxies evolve from tiny primitive structures into the star-forming giants of cosmic noon? Webb's observations reveal the transitional population, the galaxies in between. They aren't fully primitive, but they aren't structured either. They are in motion, becoming. And that is the key. They show us the universe in the act of transformation. This brings us to one of the most exciting aspects of this discovery, the future. Webb has only just begun to uncover the early universe. These 250 galaxies are merely the first major statistical sample. The telescope will soon push deeper to earlier epochs, perhaps even to within a few 100 million years of the Big Bang. When it does, we may witness the very first generation of galaxies, the primordial ancestors of everything we see. But even now, with the data we have, a new picture is forming. A picture in which galaxies are not static objects, but living systems. Systems that breathe, collide, merge, break apart, and rebuild. Systems whose histories are far more violent and dynamic than we ever imagined. And this, in many ways, is what makes the universe so remarkable. We are not living in the aftermath of a calm, orderly cosmos. We are living in the refined product of billions of years of cosmic struggle, chaos giving birth to structure, disorder giving way to beauty. In the next part of our journey, we will explore how this discovery changes the way we interpret the Milky Way's past, what it means for future observations, and how scientists will use Webb to trace the full arc of galactic evolution, from the first clouds of hydrogen to the magnificent spirals we see today. As we reach the final steps of this journey into the early universe, we begin to see the true magnitude of what the James Webb Space Telescope has revealed. This isn't just a discovery about distant galaxies, it's a discovery about us, about our origins, about the forces that shaped the Milky Way long before Earth was even a dream. For the first time, we have a clear statistical portrait of what galaxies looked like when the universe was still young, when gravity, gas, and time were sculpting the foundations of everything we know. These turbulent galaxies show us that the early cosmos was not a serene environment, gently assembling stars. It was more like a cosmic forge, heated, unstable, and full of collisions and upheaval. And yet, out of that chaos emerged order. Out of swirling, clumpy gas came the first rotating disks. Out of violent mergers came structured systems. Out of turbulence came the beginnings of the cosmic architecture we see today. This idea that beauty arises from chaos is one of the most profound themes running through the universe. It echoes in everything, from the birth of stars to the evolution of life. And now, thanks to Webb, we can watch that principle unfolding on galactic scales. So what does this mean for our understanding of the Milky Way? It means that our galaxy too was once a disorderly, unstable cloud of gas and stars, tossed and stirred by collisions and rapid star formation. The grand spiral arms we admire today are not ancient or timeless. They are recent refinements sculpted by billions of years of cooling, settling, and stabilization. When we look at these early galaxies, we're seeing chapter 1 of our own story, a story written not in calm, but in cosmic turbulence. This discovery also provides astronomers with one of the most powerful tools they've ever had for refining galaxy evolution models. Before Webb, simulations had to make assumptions about how long chaotic phases lasted, how frequently mergers occurred, and how quickly disks formed. Now we have real, large-scale evidence to guide those models. Astronomers can adjust their simulations to match the behavior of hundreds of early galaxies instead of a handful of bright outliers. This means better predictions, more accurate reconstructions of cosmic history, and a clearer picture of how galaxies like the Milky Way came to be. And perhaps one of the most exciting outcomes is how this discovery sets the stage for what comes next. Webb is capable of observing even earlier epochs, periods closer to the first few 100 million years after the Big Bang. Scientists hope to push the frontier deeper to capture galaxies so young that turbulence hasn't yet reached its peak, or so primitive that they reveal the first steps of galactic formation. These observations will help answer some of the most fundamental questions in astrophysics. When did the first disks truly begin to form? How rapidly did the earliest mergers shape structure? How did dark matter halos influence the transition from chaos to order? Every time Webb turns its golden mirrors toward the distant universe, we are looking not just backward in time, but backward into the very mechanisms that created cosmic structure. These chaotic early galaxies are not simply objects of curiosity, they are the raw laboratories of nature, the places where physics reveals itself most vividly. And there is a deeper message hidden in all of this, a human message. We are often tempted to imagine the universe as orderly, predictable, clean, but the truth is that order is the final act, not the opening scene. The universe grows through disorder. It evolves through imbalance. It shapes beauty through conflict and change. The Milky Way, your home, my home, began as a storm, and from that storm, everything else followed. As we continue studying these galaxies, we also continue learning something profound about scientific progress itself. Truth comes not from isolated examples, but from understanding the whole. By examining more than 250 galaxies instead of a handful, astronomers uncovered a pattern that had been hidden for decades. The exceptions no longer defined the rule. The rule finally emerged in full view. And that rule tells us that galaxies grow into order through chaos. This is the power of the James Webb Space Telescope. It doesn't just capture beautiful images, it answers questions that once felt impossible. It takes theories written on chalkboards and tests them across billions of light years. It reveals the universe not as we hoped it would be, but as it truly is. And that is the essence of science. Not certainty, not perfection, but discovery. As we close, remember this. Every spiral galaxy you see in a picture, every elegant swirl of stars, every glowing arc of gas is a survivor of a chaotic childhood, a descendant of turbulent ancestors, a masterpiece shaped by time. The universe is not static, it is alive with history, a history that Webb is now unveiling piece by piece. My name is Michio Kaku, and it has been an honor guiding you through this journey into the cosmic past. The story of galaxy formation is far from complete. The next revelations are out there, waiting in the faintest light across the deepest reaches of space, in galaxies still fighting to become what they will one day be. And with every new discovery, we grow closer to understanding the greatest story ever written, the story of the universe itself.